In this lecture we will see the procedure for device analysis. The topics that we shall be covering in this lecture are the continuity equation, which describes the distribution of electrons and holes when there is excess carrier generation, recombination and carrier movement. Then we will see the 5 basic equations for device analysis. We will consider some of the simplifications which are used for deriving the characteristics, how the equations can be simplified, and finally we will summarize the characteristic material parameters which describe a semiconductor device. So let us begin with the continuity equation. In the last lecture we had shown that if there is uniform volume generation within a sample, maybe for optical due to optical generation for example, then the rate of increase of the carrier concentration, here we are showing the equation for holes, similar equation will be there for electrons. So rate of increase of the hole concentration for example can be described by this equation, which says that rate of increase of hole concentration is equal to net generation rate of holes. We had emphasized while giving this equation that we assume that since there is uniform volume generation, there is no movement of carriers within the volume from one point to another point. However, in general this is not true, there will always be some movement of carriers, okay. Situation will not be uniform throughout the device. So we need to have an equation which will describe the distribution of electrons and holes in a general situation, okay. Now this is what we are doing now in continuity equation. So the general situation is depicted here. We are assuming a one dimensional case and we are considering holes. So you have holes moving from left to right in this particular semiconductor block. We will assume that the area of cross section of the block is unity. The current density Jp is different at this phase of a differential volume that we are considering and the other phase of the differential volume. So the two current densities are Jpx and Jpx plus dx. So which means the current entering the volume is not necessarily equal to the current that is leaving this differential volume, that is the volume of our observation. Now we need to write an equation describing the rate of increase of hole concentration within the volume. This can be written as follows. So rate of increase of hole concentration within the volume can be written as the net rate of input of holes as described by the difference between these two currents, Jpx plus dx and Jpx, plus any net generation within the volume. So rate of hole input into the volume, that is understood. So this is the additional term that is coming in here, okay, as compared to the situation that we described here where there was no movement of the carriers. So we can translate similarly this particular statement into an equation as follows. The rate of increase of hole concentration within the volume can be written as P into dx into 1. P is the concentration of holes, dx is the width of this volume, and 1 is the unit area of cross section. So differential of this with respect to time. We are using a partial derivative since p can vary with x as well as t. So this is equal to net rate of hole input into the volume. So the input current density minus the output current density divided by q, since the current consists of the charge also, whereas we are talking of only the concentration of the holes and not the charge concentration. And we should multiply this by the area of cross section to get the current. So that is 1. Area of cross section is unity. So this is the net rate of hole input into the volume. Okay. Please check that dimensionally this term and this term have the same dimensions. P is per centimeter cube multiplied by dx is centimeters, 1 is centimeter square. So this is simply concentration into volume, which is just the number. So it is 1 by time, that is the dimension of this. So here you can see current is ampere per centimeter square, current density, multiplied by 1 centimeter square. So it is amperes by coulomb. So again this is per second. So dimensionally these two terms are identical, plus the net generation rate within the volume. This can be written as G dash minus the recombination rate. G dash is excess generation rate, this is the recombination rate, and we will be assuming low injection level. So this is the net generation rate multiplied by the volume, which is dx into 1. Okay. So this is the net generation rate within the volume. Now we can simplify this equation by dividing throughout by dx into 1. If you do that, what will happen is this term will become dou p by dou t. This term, when you divide by dx, you find that, let me do the division here, show it here. I remove this dx into 1 and this dx comes here, this 1 unit area of cross section goes off, this dx into 1 will vanish when you divide. So this is the dou p by dou t term. This term can be written as minus 1 by q into dou jp by dou x as dx tends to 0. Okay. You are getting a minus sign because when you write the derivative, the convention is jp x plus dx minus jp x by dx, that is the derivative. So here, since these terms are reversed, you get a minus sign, plus this g dash minus delta p upon tau. So this is the so called continuity equation for the holes. It describes the distribution of holes when there is movement of holes or there is hole current, excess generation, and as well as recombination. We can write a similar equation for electrons, and that would be dou n by dou t is equal to 1 by q dou j n by dou x plus g dash minus delta n by tau, where tau is the lifetime of minority carriers. Note that this minus sign has been removed as compared to this equation. Here you had a minus sign, okay, and that minus sign is gone there. This is because if you have electron current here, if electrons are flowing into the volume, then the current is from right to left. So the current is in the opposite direction to the flow of electrons. That is why this negative sign is gone when you replace jp by jn, or when you write the equation for electrons. Now we can combine this continuity equation with the other equations we derived in the earlier class, the transport equations, okay, and then the basic equations would look something like this. So you have the transport equation for electrons, which combines the drift and diffusion. Then during the flow you have the continuity equation, okay, describing the distribution of electrons when there is generation, recombination and movement. Now note here that we have used delta n instead of n. Okay, this is to have only one type of variable in the equation. Since we have delta n here, we have put delta n here instead of n. Note that it makes no difference since delta n is nothing but n minus n naught. Delta n is n minus n naught, where n naught is the equilibrium concentration. So when I differentiate this with respect to time, the differential of n naught with respect to time is 0. Okay, so these two are identical. Okay, so we can replace this by this. That is what has been done here. Now similarly, you have the equation for holes, the transport equation, drift and diffusion, and then you have a continuity equation that we derived just now. Now this completes the picture for what is called carrier flux. Okay, equations associated with carrier flux. So these are the equations which show why the flux is caused, and these are the equations which show that the particles are conserved during flow. The continuity equation is nothing but a conservation law. Now in addition, we have the electric flux. Okay, in fact this electric flux is causing the drift current here, E. So you have equations associated with this flux also. The transport like equation, okay, this is not called transport equation in practice. Okay, people do not call this as transport equation, but here we have listed it under transport equation because it is transport like equation. Okay, because this equation shows that the electric field is caused by a gradient of potential, just as this equation shows that the electric current or carrier flux is caused by the gradient of potential or electric field. The electric field itself is caused by gradient of potential. Now since electric flux can be regarded as a flow of electric lines, you have a continuity equation associated with this. This is a so-called Gauss's law, okay, which shows the increase in the electric flux due to the space charge. So this is conservation of electric flux during flow, just like the conservation equations for carrier flux. Now this is Gauss's law, we have come across earlier in physics, so we are not describing it in great detail here. We will provide a brief explanation of the Gauss's law. So here what you find is a one-dimensional situation where electric field is going into this volume and coming out. Inside the volume you have positive space charge. The electric field that is coming out has more lines than the number of lines entering this particular volume, because every positive charge is a source of a field line. Okay, so that is why the electric field increases because of presence of the volume space charge. So we can write the increase as follows: the increase dE is due to the space charge rho in the volume. Now the total charge in the volume would be rho into dx into 1, we assume unit area of cross section. Now the flux, total flux into this area can be written as epsilon into dE into the area, because the flux is defined in terms of the displacement vector d, which is epsilon E. So differential of this displacement vector is epsilon dE. So then we can equate these two, and now when we rearrange, we cancel this one and bring this dx here and this epsilon here, you get the Gauss's law. So that is the Gauss's law shown here, equation. Now recall that we have already said that the space charge within the semiconductor rho is given by q times Nd plus P minus Na minus N, where Nd plus is the ionized donor concentration, Na minus is the ionized acceptor concentration. Okay, so sum of the difference between the positive charges and negative charges is the space charge. Now this particular these equations we can see the close correspondence between the equations for carrier flux and that of the electric flux. If you rewrite the equations as follows, the first step, we can write this E in terms of the gradient of potential to see the one-to-one correspondence between these two equations and this equation. So you can see here E is replaced by minus dou psi by dou x, where psi is the potential. So here the current is because of concentration gradient and potential gradient. The electric flux is because of potential gradient. We can achieve even better correspondence among this set of equations for carrier flux and the electric flux by rewriting the continuity equations, by putting this particular term on the left hand side and the delta n by dou t term on the right hand side. Okay? So when we do that, this is how the continuity equations look like, and now we can see Jn is the flux, and this transport equation shows the cause of the flux. Continuity equation shows the gradient of this particular flux, the cause of this gradient. Okay? So here you have the cause of the flux, and here you have the cause of the gradient of the flux. So continuity equation is giving you why there is gradient in the flux. So now you can see the one-to-one correspondence. E is the flux and dou E by dou x is the gradient of the flux for the electric field. Similarly, these two are the fluxes for carriers and these two are the gradients of the fluxes. So in this form, the close correspondence between the 6 equations is seen very easily, and therefore it is very easy to remember these equations. Now however, what you find is all these 6 equations are not independent. In fact, there are only 5 variables in this equation which are coupled. That is the concentration n of electrons, concentration p of holes, then the Jn, the flux of electrons, and Jp, the flux of holes, and the electric field, which depends on again the concentration of holes and electrons. So N, P, Jn, Jp and E are the 5 variables, okay, which are independent, and psi can easily be obtained once E is obtained, and that being the case, only the 5 equations are coupled. So E equal to minus dou psi by Ax, that equation has been removed, and basically you only have these 5 equations to be solved simultaneously. Once these equations are solved, you can always get the potential. So this is what is shown here in a summary. You have the 5 basic equations, Jn transport equation, Jp transport equation, Jn continuity equation rewritten in the form in which it was derived, and Jp continuity equation, and then the continuity equation for electric flux or the Gauss's law. And so you have 5 variables to be solved for, that is N, P, Jn, Jp and E. Once you have solved these variables simultaneously using these equations, then you can get psi from electric field using this particular formula. Now these equations look fairly complex, and so we need to discuss how they can be simplified in different physical situations. Before we take that up, it would be useful for us to see how these transport equations on the slide, that is equations for Jn and Jp, can be represented in a compact form using the quasi-Fermi levels. So for example, let us take the equation for the electrons. Jn is equal to Qn mu n E plus Q dn dou n by dou x. How do we represent the right hand side using quasi-Fermi level in a compact form? So we start with the equation for n. Using the quasi-Fermi level concept, we can write n equal to nc exponential of EC minus EFN by KT with a negative sign. This is the quasi-Fermi level for electrons. Now let us perform this operation dou n by dou x and see what we get. So dou n by dou x is equal to Nc upon Kt into exponential of EC minus EFN by Kt with a negative sign multiplied by the differential of this with respect to x, and that is dou EFN by dou x minus dou EC by dou x. So 1 by Kt has been taken out already in this differential. Nc into exponential minus EC minus EFN by Kt is nothing but this n itself. So this turns out to be nothing but n upon Kt into dou by dx minus dou EC upon dou x. Now if you multiply this dou n by dou x by q times dn to get this particular term, so we will multiply this by q times dn. So here you will multiply by q times dn, and here you will multiply by q times dn. Now what you find is this q can be shifted below, and you can write this as Kt by q. This is nothing but the thermal voltage Vt, and dN by Vt is nothing but mu n by the Einstein relation. So one can replace this term dN by Kt by q by mu n, and you get this as the expression for the diffusion current q dN dou n by dou x. Now one can add this term to the drift term qn mu n E, where E should be written in terms of the conduction band energy. So we can write q n mu n into E, the drift current, can be written as q n mu n, and E is nothing but 1 by q dou EC by dou x. We have shown this earlier, that EC by q is the potential energy corresponding to the electrons in the conduction band, and gradient of this potential is the electric field. The negative sign is not there because EC is the electronic potential energy. So this q gets cancelled, and we find that this drift current is n mu n into dou EC by dou x. Now when you add up this and this, that is we are adding up this and this to get this, you find that n mu n dou EC by dou x will get cancelled here because this has a negative sign here, and what we will be left with is only mu n n dou EFN by dou x. So let us write that here. You get the equation Gn is equal to q, sorry, the q is not there, the n mu n dou EFN by dou x. That is the compact expression for the electron current in terms of the quasi-Fermi level. So now you can understand why the quasi-Fermi level is a powerful idea. So the gradient of the quasi-Fermi level contains information about the drift as well as diffusion. Okay, that is what this shows. One can similarly show that Jp is equal to P mu P dou EFP by dou x. That is, the whole current depends on quasi-Fermi level for holes, the gradient of that. Now these are the compact forms of the transport equations in terms of quasi-Fermi level. These will be useful for us as we will see subsequently. Now we will take up the various physical situations in which we can show how these equations can be simplified. Let us take the condition of equilibrium. Under equilibrium, Jp is 0 and Jn is 0. because according to the equilibrium state, for every process there is an inverse process going on at the same rate. There cannot be any currents either for holes or for electrons. Further, there cannot be excess carriers, so delta n is equal to 0 and delta p is also equal to 0. Now as a result, what happens is that the continuity equations that you see here in the slide, these become trivial because delta n is 0. So this term goes off and this term also goes off. There is no excess generation, so this term goes off. So all the terms become 0. So this is trivial. But the transport equations may be non-trivial because all that we are saying is Jn is 0, that is left hand side is 0 in these two cases. So which means that there may be right hand side terms, but they are cancelling each other. Okay? So either individually these two terms are 0, these two terms here are also 0, or these two terms and these two terms are cancelling each other. So drift and diffusion are in balance if there is an electric field and concentration gradient. That is what it means. Now if you try to interpret this particular situation Jp0, Jn0 in terms of the quasi-Fermi levels, then what do we get? We get an important information, and that is the gradient of the quasi-Fermi levels is 0. So dou AFN by dou x is 0, dou EFP by dou x is also equal to 0. This means EFN and EFP are constant with x. Now under equilibrium we know EFN is equal to EFP equal to EF. So these imply that the gradient of the Fermi level is 0. Okay, since EFN is equal to EFP in equilibrium. As we will see, this is an important starting point for drawing energy band diagrams under equilibrium for non-uniformly doped semiconductors, that EF is constant with x. Incidentally here EFN is equal to EFP is EF. We have to write that this is equal to EF. Let us consider now another situation, and that is if the drift and diffusion currents, which are exactly in balance under equilibrium, are individually very large, but they are slightly in imbalance. So this means, for example, if I write for holes, it is like this: Jp is Qp mu p into E minus Q dp dou p by dou x. So imagine a situation where these two quantities are large, but their difference, that is Jp, is very small. So this is, let us say, 1000 units and this is, let us say, 995 units. So 1000 minus 995 is 5. So left hand side is 5 units. So 5 is very less than either 1000 or 995. So we are talking of a situation where Jp, the magnitude, is much less than Qp mu p into E, the magnitude of this, and the magnitude of Q. I am concerned with the magnitudes because the signs have to be taken care of. Okay, so we are only interested in the magnitudes. If this is satisfied, then we can write Jp is approximately equal to 0. So whether we say this is 1000 and this is 1000, in which case this is exactly 0, or in the other case this is 1000, this is 995, this also, the difference is almost 0 compared to the individual magnitudes. Please understand this very carefully. Okay, so what we are saying in our example is 5 is equal to 1000 minus 995, that is what we are getting, and we are saying that this 5 can be neglected and made equal to 0. Okay, so we are writing this as this, the difference is almost 0. So please note that unless these two quantities are very large, we cannot neglect the net result coming on the left hand side. So in some situations this kind of approximations may enable us to find out these two quantities. So this kind of situation is called quasi-equilibrium. So you can have a similar situation for electrons. For electrons, again, if Q n mu n E and Q dn dou n by dou x, if the magnitudes of these two are much greater than Jn magnitude, then we can write Jn approximately equal to 0. So these are small disturbances from this equilibrium, Jp equal to 0 and Jn equal to 0. Okay, these are valid when drift and diffusion are large compared to the net current. Okay, so these approximations hold when drift and diffusion are large and in opposition. And this kind of situation is called quasi-equilibrium because they represent a small disturbance from equilibrium. Okay, so this approximate equal to sign is interpreted as quasi-equilibrium. So this is another kind of situation, okay, which can come about in devices. Now, an example of this situation where the drift and diffusion are large and in opposition is near the junction of a p-n junction. So you have a p-n junction, near the junction there is a region in which you find charges and electric fields giving rise to large drift currents, but also there are gradients of concentrations giving rise to diffusion currents. So under equilibrium in p-n junction or small voltages applied, even for small voltages applied to the p-n junction, you will find this kind of situation holding. Okay, we will discuss the p-n junction in detail. I am only giving you an example of a situation where this approximation can be applied. Now let us interpret this Jp approximately equal to Jn approximately equal to 0 in terms of the quasi-Fermi levels. Okay, so if you interpret in terms of these, you will get instead of this equal to sign and approximately equal to sign. So under this kind of quasi-equilibrium condition, you will have dou Fn by dou x approximately equal to 0 and dou Fp by dou x approximately equal to 0. So which means that for the quasi-Fermi levels there will not be any gradient, or the gradient will be very, very small. So Efn and Efp will be constant with x. However, please note, since this is not an equilibrium state, Efp is not equal to Efn. Okay, so in terms of the quasi-Fermi level, this quasi-equilibrium condition can be interpreted using this. This is also a very useful piece of information. Okay, when drift and diffusion currents are very large and they are in opposition, then if you were to draw the quasi-Fermi levels in such a region, they will be constant with x, although they will not be identical. Okay, so you will have to draw two parallel lines. We will see this when we analyze the p-n junction. Now let us discuss another example of a situation where simplification is possible of the equations, that is we can simplify the equations, that is the steady state. In steady state, basically dou delta p by dou t is 0 and dou delta n by dou t is 0. This is the definition of steady state, that is all processes are constant with time, so there cannot be any quantity that is changing with time, so derivative of quantities with respect to time will be 0. So which means in the continuity equation shown in this slide, these left hand side terms are 0. Now what about the right hand side terms? Okay, so they can exist, but they will all add up to 0. That is the meaning of the steady state. An important result for the steady state is obtained by taking the difference of these two equations. So because left hand sides are 0, when you take the difference, what will happen is that since this g dash for electrons is same as the g dash for holes, because excess electron hole pairs are generated, the excess electrons and holes are generated in pairs, and similarly excess electron concentration is equal to excess hole concentration. So when you take the difference of these two equations, the left hand side is 0 and right hand side, these two terms will cancel, leaving behind a gradient of the sum of Jn and Jp. So you get dou Jn plus Jp upon dou x is equal to 0. This is obtained by adding continuity equations, or rather by subtracting continuity equations. For holes and electrons. So this is a very important result. It means that if you write Jn plus Jp as the current flowing through the device, total current, because sum of the electron and the hole currents, so we get the important result dou J by dou x is equal to 0. So in a one dimensional situation, the current will be constant with x, even though individually the electron and hole currents may vary with x, okay, but their sum is constant with x. This is what this shows. This is a very important relation in steady state, which will help us in analyzing the devices. Now, like there is a small disturbance of the equilibrium state, and that is this quasi equilibrium, you can have a small disturbance of this steady state, that is called the quasi steady state or quasi static state. Okay, so quasi static or quasi steady state would be described by equations, namely this is approximately equal to 0 and these two are also approximately equal to 0. So now the meaning of these approximately equal to 0 should again be understood, because in the continuity equation you find that this term, look at the slide, these terms are obtained by summing up several terms. So when we are saying that this term is approximately equal to 0, it means that right hand side terms can be grouped together into one large positive term and another large negative term. The magnitudes of the positive and negative terms are very large compared to the difference between them, which is giving rise to the dou delta p by dou t and dou delta n by dou t terms. Okay, that is the meaning. This is what we had explained even in the case of quasi equilibrium, that is the individual terms are much larger than the difference. Now many transient situations can be analyzed using this quasi-static approximation. So this enables you to use the picture obtained under steady state conditions even for analyzing the transient conditions. We will see this later. Next we will discuss another physical situation that we encounter in analysis of devices. In some regions of the device, the diffusion current for a particular type of carrier, that is either for electron or for the hole, dominates over the drift current. So this is called the diffusion approximation. The diffusion current dominating over drift. Let us consider the example of holes. So if diffusion current dominates over drift, we can neglect the drift and we can write Jp is approximately equal to minus q dp dou p by dou x. So we will write here diffusion much greater than drift. Okay, we are taking the magnitudes so that the sign confusion is not there. Now an example of a situation where this kind of thing is valid is when low injection level prevails in a region of the device. We find that the excess carrier concentration, or rather the minority carriers, can be described by this particular approximation. So for example, this kind of approximation will hold for an n-type semiconductor, it will hold for holes in an n-type semiconductor. Why? This is because the drift current depends on the concentration of carriers and the electric field, whereas the diffusion current depends only on the gradient of the concentration of carriers. So if the concentration of carriers is small, then the drift current tends to be small. Okay? So you can have a situation where the gradient of the concentration of carriers is large, but the concentration itself is small. Now this will not hold for majority carriers. This kind of approximation that drift very small compared to diffusion may not hold for majority carriers because the concentration of majority carriers is very, very high. So the drift current for these carriers is high. So we will write here may hold for holes in n-type semiconductor under low level conditions. So we can generalize and we can replace holes by minority carriers, and we can say may hold for minority carriers. Under low level conditions. This is a specific example of an n-type semiconductor. Now let us see what is the consequence of this. If the transport equation can be simplified for holes in this form, then what does it imply on the distribution of the holes or excess holes as a function of distance and time? Now let us look at the continuity equation for holes. This is given here on the slide. So this equation now we can write. We can simplify the dou Jp by dou x term using the diffusion approximation, and we will get dou delta p by dou t can be written as dou Jp by dou x. You have to differentiate this. So dp dou square p by dou x square. The q has got cancelled and you have a negative sign here. Actually this negative sign will also get cancelled because there is a negative sign in the expression for Jp and there is a term negative sign here in the equation for the continuity against Jp. So the negative sign gets cancelled, so this sign will not be there. So plus g dash minus delta p by tau. So that is the equation. Okay. Now further let us assume steady state condition. in which case this term will drop out. So under steady state this equation reduces to zero is dp dou square p by dou x square plus g dash minus delta p upon tau. Now this p is p naught plus delta p. If you further assume that the semiconductor we are talking about is uniform, and as a result if p naught is uniform, this may be due to uniform doping. So that is same as saying doping is uniform. Okay, that is uniform doping. So if that happens, p naught is uniform means p naught is constant with x. When you differentiate with respect to x this term, the differential of p naught will go to 0, and then you will have dou square p by dou x square is the same as dou square delta p by dou x square. Okay, and therefore this equation can be rewritten as dp dou square delta p by dou x square plus g dash minus delta p by tau is approximately equal to 0. Now we can simplify this particular equation and write it as, so what we do is we divide by dp throughout and these two terms we club. So we will get equation of the form dou square delta p by dou x square is approximately equal to minus of g dash tau minus delta p upon dp tau. Okay, and this is we can write this actually delta p minus g dash tau, that is simple. Let us write it in this form. So this is the equation. Now we note that if g dash is uniform, if g dash is uniform, which means g dash does not change with x, then we can replace this delta p by delta p minus g dash tau, so that everything will come in terms of one variable, because differential of g dash with respect to x would be 0. So if g dash is uniform, then the above can be written as dou square delta p minus g dash tau upon dou x square is approximately equal to delta p minus g dash tau upon dp tau. Now incidentally, this tau is the lifetime of minority carriers, and since we said that the diffusion approximation holds generally for minority carriers, we can always identify this tau as the tau p. Okay, so we can write this tau as tau p, the lifetime of holes, because holes are going to be minority carriers, because we are writing this diffusion approximation for holes. So we can replace this tau by tau p. Now from here, by comparing the two sides, it is very clear that this term has dimensions of distance square. Okay, dp is centimeter square per second and tau p is second, so when you multiply you will get centimeter square. This has dimensions of length, and this length is denoted as capital L suffix small p and square of that. It can be physically interpreted as this particular length can be physically interpreted as the length over which a hole travels by diffusion before it recombines, okay, and that is why this is called the diffusion length. The LP is called the diffusion length of holes. So this is the minority carrier diffusion length. Now how do you show that LP is the length over which a hole travels before it recombines, okay, when diffusion and recombination both are present? It can be done in the same way as we have done for lifetime, okay. How did we show that if there is an exponential decay of a particular particle concentration, then the time constant of this exponential decay is the average time for which a particle in this population that is decaying stays. In a similar way, one can show that a solution of this differential equation is exponential in nature, and in that exponent you will have the LP coming in, okay. So let us show how the solution looks like for this differential equation. Now for a differential equation of the form dou square y by dou x square equal to y by LP square, the solution is given by y equal to a e power x by LP plus b e power minus x by LP, or you can also write it in the form c cosine hyperbolic x by LP plus d sine hyperbolic x by LP. So you can use any one of these forms, that is either in terms of exponentials or in terms of hyperbolic sines and cosines. So one can easily see by substitution here that this equation is a solution of this equation, okay. So when you double differentiate the exponential, you get an exponential itself. That is what is the key here. What you find here, when you differentiate the y function 2 times, the form of the result should be the same as y itself. That is what this shows, and that property holds for an exponential function or for a hyperbolic function, which is nothing but sum of exponentials. Now here for us y is nothing but this y and this y, these are nothing but delta p minus g dash tau, okay. So here therefore this y is delta p minus g dash tau. So that is the form of the solution. Now how do you decide whether you must choose the exponential form or the hyperbolic form? To see this, let us look at the graphs corresponding to these two exponentials and these two hyperbolic functions. These graphs are shown here. So exponential minus x by LP goes to 0 at extending to infinity, exponential x by LP goes to 0 at extending to minus infinity. On the other hand, the cosine hyperbolic function, the value is 1 at x is equal to 0, and then it rises for x positive as well as x negative, okay, and this value is 1 here. The sine hyperbolic function on the other hand, its value is 0 at x is equal to 0. It rises to positive values for x positive and it goes negative for x negative. So these are the features of these functions which will enable us to decide in a given situation which form of the function should be used. For example, supposing you have an infinitely long semiconductor, then in that semiconductor, so let us say this is your semiconductor and this is very long, let us say it goes from x is equal to 0 in this direction to infinity. Now in this semiconductor, the excess carrier concentration has to be 0 at least one of the ends, because if it is non-zero over the entire block, then this would mean that infinite number of excess carriers, okay, because the length of the block is infinitely long, and if the excess carrier concentration is non-zero all over, then there are infinite number of excess carriers, and this is not possible. So generally for very long or infinitely long semiconductor blocks, this particular function, okay, has to be 0 at least one of the ends, and therefore it is the exponential form of the function that must be used to describe excess carrier concentrations in infinitely long blocks. On the other hand, if the length of the block is finite, so if this end is x is equal to w, where w is not infinite, then it is this hyperbolic, one of these two hyperbolic forms which will be useful. So if in this block you find the boundary condition is that excess carrier concentration is 0 at one of the ends, then evidently it is a sine hyperbolic function that is appropriate. On the other hand, if at both these boundaries the excess carrier concentration is not 0, then cosine hyperbolic function is more appropriate, okay. So in this fashion, depending on the situation, one must choose the appropriate forms of the solution. Although in principle you can use any of these forms to describe any situations, okay. If you want a simple form of the solution, that is you want one of these terms to drop out, okay, you don't want both the terms, then you must follow the guidelines that we have just discussed. So infinitely long blocks, exponential form of the solution, it will be either this function or this term. On the other hand, for finite blocks, you use the hyperbolic form of the solution, and it will contain either this term or this term depending on your boundary conditions. Now in the next class we will discuss further on the implications of this particular form of the solution for the diffusion approximation, and we will consider the other approximations of the equations that are possible. I find that one of the students has a question. Let us see, what is it?
Sir, this is on the figure explaining the Gauss's law. Why are the field lines emanating from the positive charge in the differential volume directed rightward?
Your question is about this figure. Why are these lines coming out of the positive charges within the volume in this direction? Why can't some of these lines be in this direction? The reason is very simple. We are assuming that all the field lines are terminating on negative charges which are present on the right hand side here. That is the reason.